If you would recall, we've been looking at making changes to our base model cosine and sine graphs. Our base model cosine and sine graphs have amplitude of 1 and a period of 360 because we're still playing the trigonometry game in degrees. We also have some default starting places. Cosine by default starts at the top, and sine by default starts at the middle going up. What we saw was that if we make changes by multiplying, we're going to produce a stretch or a squish. We also notice that if we multiply by -1, we'll produce a reflection. We didn't do multiplication by -1 before the trig function, but the other thing that we noticed is that if we perform an operation before the trig function, like that b in both cases, is multiplication that takes place before the trig function, that's going to produce a horizontal chain. So multiplying theta by b means we had to adjust the period by dividing by b. Our default is 360. We divided by b. So we squished the graph in or stretched the graph out. Squish the graph if b is bigger than 1, and we'll stretch the graph if b is less than 1. Then we apply the trig function, and then we have this other multiplication, this time on the outside after the trig function, multiplying by a. Multiplying by a produced also a stretch or a squish because multiplication, but this time, since it happened after the trig function, it was vertical. Also, when we multiplied by something bigger than 1, that stretched things out, and when we multiplied by something less than 1, that squished it down. So it seems like with the operations that happen before, the horizontal ones, it's kind of like we do the opposite. I multiplied by 2, but we divide the period by 2. If we multiply after by 2, we multiply the amplitude by 2. It stretches. Question? Yeah, multiplying by -1, where we're changing the start value, that's based on the value of a. Because the difference there is if a is positive, sine starts at the mid going up, and then when a is negative, sine starts at the middle going down. So that's the reflection over the x-axis. So multiplication by -1 after the trig function produces a vertical reflection. Vertical because it's taking place after the trig function, reflection because that's what multiplying by a negative does. See, it's all very organized. You just got to see how it's organized. Although we didn't do any examples where we multiply by -1 beforehand, we can combine the two. We multiply by -1, that makes a reflection. And if we do that before the trig function, that means we're going to reflect horizontally, because that's how it works. That's how things go together. Just think about the order of operations. If we make b a negative number, the negative part is going to make a reflection. Since it's before sine and cosine, it's going to be a horizontal reflection. So the mirror will be side to side instead of up and down. Trig functions do weird things when you start reflecting them that way. It's like, oh, well, we might as well just use cosine. Or we might as well just use sine and not worry about the negatives. But that's good. Any other questions? Before is horizontal, after is vertical. Multiplication is stretching. Multiply by a negative for a reflection. Now the question is, what does addition do? So for that, we're going to jump over to our graphing calculator. Not our Texas Instrument graphing calculator. They're terrible graphing calculators. We are going to jump over to Desmos, our favorite graphing calculator. So here we see the graph of sine of x, and I'm just going to put in sliders for C and D. I'm going to put a plus C. That's addition that's taking place before the trig function. Think the order of operations. First thing that we do to x is add C, then we do the sine, and then we'll put a plus D outside. Plus D. Desmos is cool because it says, hey, are you going to be changing the values of C and D? And I'll be like, yeah, totally. So I would like to add sliders to all of them. I'm going to put them back down to 0 on both. I'm also going to decrease the range. We don't need to go this far. So notice that we just get, I'm also going to put in the graph of regular sine without any adjustments. Now we're going to see what happens if I make an addition before the trig function. So I'm going to adjust the value of c, change what I'm adding before the trig function. Notice that the shape is staying the same, but it's moving from side to side. The period is staying the same. The amplitude is staying the same. What's happening is all of our points are just shifting from side to side. Now I want you to concentrate very heavily on the red line moving back and forth relative to the blue line. Switch to soothing voice. Focus on the red line as it oscillates back and forth. I'm not trying to hypnotize you right now. Just kidding. Actually, no, I'm kidding. I'm not trying to hypnotize you. I can't remember what I just said. Okay, stop. So it looks like when I do that addition before the trig function, we saw a horizontal thing happening because that addition was taking place before the trig function. What do we predict is going to happen if I start the d moving up and down? I really need to pick a different letter. What's going to happen if I start changing the addition after the trig function? We're going to take the same shape, same amplitude, same period, and we're just going to move it up and down. Let's find out. Let's see what happens to the red line now. Just as you predicted. I love it because math is just so predictable this way. We know exactly what's going to happen. So this addition seems to produce a shift. It's just taking the same shape and moving it up and down for addition afterwards and side to side for addition before. I landed on the 0. I was missed by a couple of times. So we're maintaining the same shape. The way we're going to describe this is a horizontal or a vertical shift. Shift side to side or up and down. Sometimes you'll see a horizontal shift described as a phase shift. Don't describe it as a phase shift. We need 2 things to describe one as being out of phase for technical reasons. We're just going to call it a horizontal shift because that's how we're dividing things. Horizontal is stuff that's before, vertical is stuff that's after. Or we could turn both on. And then it's a screensaver from the 90s. Or your DVD player. It's actually too regular for that. I'd have to adjust them. Stop. So let's jump back into our. So when we change our multiplication to addition, where multiplication produces a stretch or a squish, addition is producing a shift. We maintain the same shape, amplitude and period, but we just move it side to side or up and down. Maintain the shape, just move it side to side or up and down. Horizontal shifts happen with addition before the trig function. Vertical shifts happen with addition after the trig function. Any questions? This is all very organized. Multiplication produces stretches or squishes. Addition produces shifts. Operations before the trig function will make horizontal changes. Operations after the trig function will make vertical changes. Let's look at a particular example. Let's jump back over to the Desmos. I'm going to set C and D to some fixed numbers instead of having them move back and forth, so no one thinks I'm trying to hypnotize them. Because I'm not going to be so blatant about it and hypnotize you with the thing I expect you to look at. I'm going to use the sound of my voice to hypnotize you while you're distracted by looking at this. So look at the nice serene. I don't think it's serene. That's a reference to the X-Files, a show that I don't think anybody has seen. Has anybody here seen the X-Files? There's one where a dude can control your mind. Let's talk about serene. That's not a spoiler. I mean, that they pretty much state that right in the beginning. So I'm going to put a value of D in there. D is going to go up to +2. And I'm going to put C at +1. Oh, hang on a second. What's going on here? When I put D at +2, which way did it go? It went up, right? So when D it went up. When D goes up, the graph goes up. But what happened when I moved C? Come on, 2, 2, 2, go to 2. I went too far. But when I moved C up to 1, which way did it go? It went to the left. So the +1 after went up, but +1 before went left. Is that weird, or does it fit with what we've observed before? So here's C at 0. And if I start moving C up, add 1 to C, it moved to the left. And when C is -1, look, if I make C -1, which way did it go if I move C to -1? Now it's going to the right. If I make D equal to -1 or -2, then it moves down. That makes sense, right? Plus is up, minus is down. And C is like, oh, nah, I'm going to be different. When you say plus, I'm going to go to the left. When you say minus, I'm going to go to the right. That's not how this is supposed to work. Or is it? Did anything like that happen before? Think about multiplication. We had A times a cosine of B times theta. How do we take that multiplication by B and adjust the period? What do we do to find the period? We took our default period of 360, and what do we do with the B? We divided by 2, even though the equation says multiply by B. It happened before, and we divided 360 by 2. So this kind of makes sense. When we have a +1 before the trig function, we go to the left. If I have a -1 before the trig function, we go to the right. But the stuff after does exactly what it says on the tin. When I put +2 after the trig function, it went up. The graph goes up. When I put +2 after, or -2 after the trig function, the graph went down. Cool. Let's go back and summarize that. So if we had, for example, maybe another page. So the observation, let's summarize it this way. The horizontal changes seem kind of backwards. So for example, if we have y equals sine of theta plus 1 plus 2, this plus 2, let's see. This plus 2 moves the graph up. That plus 2, it's a vertical shift, and the graph went up 2. But even though it says sine of theta plus 1, that plus 1 represents a horizontal shift because it's addition and it happens before. That's a horizontal shift that goes left 1. Once we get used to this kind of structure, it makes a lot more sense. But in the beginning, it feels backwards. That's why I'm pointing it out this way. We don't want to finalize our understanding of this by saying the horizontal stuff is backwards. It just feels backwards because we're new to reading these changes in function. I don't want to go that big on my shift. Too much shift. When you put too much shift in, that's called a fast and furious mistake, because there's too much shifting. Have you seen Fast and Furious, that first movie? They're in like a quarter-mile drag race. They shift like a dozen times. How short is your gearing that you're in 12th gear by the end of a quarter-mile drag race? It's ridiculous. You know what I mean? Set the car up to drag race, make one really long first gear, then you don't have to shift. Or it's 2022, just make it electric. By the way, if you find yourself drag racing someone in an electric car, just be like, all right, I'll drag race you. Best 9 out of however many you. So don't just do it once. Say, okay, but we have to drag race 10 times. Actually, that might not be enough. We have to drag race 20 times. Or better yet, say, okay, I'll race you to New York. Oh, it takes me too long to fill up. But then if you have an electric car, just be like, okay, I'll drag race you till your exhaust chokes us all to death. No, but I need a twin turbo V12. Anyway, too much shifting. I just want this to be 10. That's actually kind of a lot of shifting for this one. What we want to do is read the order of operations so we can see what happens before the trig function, then what happens after the trig function. And this has a full suite of changes. I've got my sign in the middle. I've got some stuff. I've got some multiplication and some addition that happens before the trig function and stuff that happens after the trig function. So let's list the things that happen that turn theta into y. So we start off with theta, and the first thing that we do is we're subtracting 10. That's going to be addition that happens before the trig function. Next, after we do theta minus 10, we multiply the result by 3. So I just got some shorthand for what happens next. Next, multiply by 3. Third thing that happens is the trig function. So third, we do the sine. And now the stuff that happens is going to be after. I've got a +5 and a minus times -7. So we got to think of our order of operations. We take care of the multiplication first. We don't want to do 5 minus 7 because it doesn't say 5 minus 7. It says 5 minus 7 of these things. So there's no 5 minus 7 in this. It's 5 minus 7 times something. So there is not a -2 going around here. So the next thing that happens is we multiply by -7. And fifth, we add 5. That's how theta gets turned into a y. So we see we've got 2 horizontal changes and we got 2 vertical changes. These happen before the trig function. So these are our horizontal changes. And these happen after our trig function. So these are our vertical changes. Here's our middle. Now let's list all the stuff, what happens. That -10 is going to be a horizontal shift because it happens before, so it's horizontal. And it says -10. And even though minus is supposed to be to the left, it's horizontal changes, so it's going to be right 10 units. So that -10 represents a horizontal shift 10 units to the right. Multiplication by 3. Multiplication before adjusts the period. And so this tells us that the period will be 360 divided by 3. So the period is going to be 120. Remember, the horizontal stuff feels backwards. We take the period, the base period of 360, the default period of 360, and we divide it by 3, even though the function said multiply by 3. Then sine happens, and now we're into our vertical changes. In the vertical changes category, I've got a multiplication by -7. It's going to do 2 things. First, our amplitude is going to be the absolute value of the -7, or just 7. And furthermore, since it's negative and we have negative sign starts at the mid going down. And finally, the +5, it's after, it's a vertical change, and plus an addition makes a shift. So it's going to shift, a vertical shift up 5 units. I know this is the first example coming out of the gate with all the changes, and I put all the changes in. But this is as far as it goes. This is as complicated a function that I'm going to ask you to analyze. I'm going to use addition and multiplication, and that'll happen before the trig function or after the trig function. So horizontal and vertical, and you just have to know which way to shift, calculate the period, calculate the amplitude, and decide where to start. 5 things to figure out. Any questions? How's everybody okay? Everybody looks very sad. It only seems like it's a lot to remember because it's a lot to remember. You have to remember all of it all the time in perfect detail. All right, so that does seem like a lot. I don't know what math classes your future holds, but you still have to remember all this later. So it's not like you could forget it at the final. You have to remember it later. Sometimes you get warning though. Like when you're in my calculus class later on, I'll be like, well, hey, remember graphing trig functions? And then you'll be like, oh, is there a quiz on graphing trig functions today? And I'll be like, oh, no. And then you'll be like, oh, then I totally remember graphing trig functions. And then you'll be like, oh, hey, Siri, make a note that I should remind myself how graphing trig functions work. And I'd be like, oh, what? What? No, it's fine. Just go back to the lecture. I totally remember that stuff. Think about what this graph will do. Now, normally, if I'm going to draw this graph, normally I've got this, I got the start, and I'll go, let's see, 1, 2, 3, 2 up, 1, 2, 3, back to the middle, 1, 2, 3, down to the bottom, 1, 2, 3, back to the middle. Now, normally, sine would have this shape, middle, top, middle going down, bottom, middle going up. But I'm going to be starting at the middle going down. So I'm going to put a couple more. 1, 2, 3, back to the top. 1, 2, 3, back to the middle. Now, this is where I'm going to have one cycle. So I want to make sure I get my start at the middle going down. They're rearranging. I think upstairs is possible. Be careful. All right. Now, let's take care of our vertical stuff. Normally, our middle is at 0. And let's talk about the middle first. Normally, our middle is at 0, and we just do up the amplitude and then down the amplitude. The amplitude is still going to be the same. Our amplitude is still 7. So the distance from the top to the middle is still 7. And the distance from the middle to the bottom is still 7. The amplitude is always the distance from the middle to the top. But we've taken all these numbers and we've shifted them up 5. So instead of the middle being at 0, the middle is going to be at 5. So the middle is going to be at 5. Normally the middle is at 0, but we shifted up 5 units. So we're just going to put the middle at 5. 5 up from the middle means the top is going to be at 5 plus 7. Or 12. And the bottom will be at 5 minus 7. Negative 2. We've used our vertical information. Remember, see what I did there? I color coded it. Our vertical shift is just going to tell us where the new middle is. Our amplitude works the same as the amplitude always works. It's the distance from the middle to the top and the middle to the bottom. Next, we got to deal with horizontal stuff. Let's start with the period. And the period is just the how far it is from from our starting point to the next similar point. So our period is going to be 120. So each quarter of the period, each quadrant or quarter of the period is going to be 1/4 of 120. So half of 120 is 60, half of that is 30. So a quarter period so these points, our named points, are 30 apart. Normally, that would mean these points are at 0, 30, 60, 90, 120. Normally, that means we'd be at 0, 30, 60, 90, and 120. But that's not the only horizontal thing that's happened in this function. What other horizontal thing happened in this function that's going to change these 5 values? We've taken the 0 and we need to shift it right 10. We need to take all 5 of these and shift them right 10. So 0, I'm going to have to add 10 to all these. So instead of this start at the middle going down, being at 0, 5, it's going to be at 10, 5. Instead of this point at the bottom being at 30, -2, this point is going to be at 40, -2. Instead of this point in the middle being at 60, 5, it's going to be at 70, 5. Instead of this point at the top being at 90, 12, it's going to be at 100, 12. And finally, this last point, the 5th point being at, instead of 125, it's going to be at 135. Then we just have to connect the dots in a nice sinusoid. And we're just going to go a third off the middle for our halves. A third off the middle is at a half. A third off the middle is at a half. And then that's how we're going to get our nice sine. Now, of course, this continues going on forever, but I'm always going to ask for is one cycle, and I'm going to ask you to label 5 points. One cycle will have 5 points. Middle going down, bottom, middle going up, top, middle going down, bottom, middle going up, top. 5 in order. I suppose you could just like make a whole bunch of cycles and just label 5 tops. But I want 5 points labeled in one cycle. I want you to show me where that cycle is. Any questions? Is that okay? This one example has kind of has it all. Has all the things that we want to do. Got a horizontal shift, a change to the period, an amplitude, a reflection, and a vertical shift. How's everybody okay? Everybody looks super thrilled that you know this information now. This is what you look like. I'm just gonna go ahead and assume that that's like this is awesome thing. I can just imagine everybody watching Infinity War. Captain America like grabs Mjolnir and everybody goes crazy and you all give me just like, that was everybody's reaction. That's how it happened, right? It's like, oh, this is like one of the most awesome moments in this entire series. It's like, oh, wham! Captain America standing there. And Thor's like, ah, I knew it. And the whole crowd just like goes crazy by making this face. That's the way I remember it. By the way, not a spoiler. I know that that movie is only like a couple of years old, but was it like 4 years old, 3 years old? 4 years old. It's only a couple of years old, but I mean, the MCU is really part of the cultural zeitgeist. And if you haven't seen it by now, you're just going to miss out. Like there are certain things that just no. Like Darth Vader is Luke's father. Everybody knows that now. If you didn't know that, you don't get to have that anymore. That spoiler has gone past its statute of limitations. You can just go ahead and say that Darth Vader is Luke's father. And if anybody's like, oh, come on, man, I haven't seen Empire yet. You just be like, oh, dude, that movie came out like 40 years ago. Get with it. But things that are like the size of the movie dictates how big the statute of limitations is. The MCU is going to have a short statute of limitations. I haven't seen Thor: Love and Thunder, so if someone goes around talking about a spoiler from Thor: Love and Thunder, just because I haven't seen it yet, I think I'm past the statute of limitations. I should have seen it by now if I want a spoiler-free viewing of the movie. As if you can't tell what's going to happen in an MCU movie. The whole point is that you know exactly what's going to happen in an MCU movie. They deliver, and you're like, oh, yay! We knew that at one point, Captain America was going to have Mjolnir in his hand and start smacking Thanos with it. We knew that that was going to happen, but still when it happened, we're like, oh, yay! Because, I mean, that was cool. Do you know what I mean? Like in Lord of the Rings, also a movie that's like 1,000 years old. So And that's also based on a book that came out in like what, the 30s? Like it still gets me when Gandalf is like, "Oh, fly, you fools," and then falls. I'm still like, "Oh," even though I knew exactly what was going to happen. I don't know how they were going to represent it on the screen or how he was going to deliver the line, but I knew it was going to happen. Like, "Oh, fly, you fools." And I'm like, no. You know what I mean? All right, let's take a break. Come back, talk more about sinusoidal functions.